Welcome to Industry Insights with AIM Solder, a video and podcast series where we dive deep into the world of soldering and electronics assembly with the industry's top minds. I'm your host, Gail Towle. Today we are talking once again with Dave Hillman. If you recall from last time, Dave has been in the field for over 3 decades, working at Collins Aerospace, won all sorts of accolades, participated in all sorts of organizations, and is generally a brain worth picking, and that's what we plan on doing. So today we are discussing adventures and advice in electronics assembly, and we're going to sort of dig a little deeper into some more specifics. And let's start with what are some key considerations when selecting solder materials for different applications?
Well, that's always a fun one, Gail. I think there's a couple. One, you should do some testing. And I don't have to, if I'm going to get a solder from AIM, you give me a wonderful technical data sheet. I don't need to redo the IPC quality tests or anything, but how does that work in my product? Have you talked with the design team? I think the other thing is, we don't need elegant solutions for simple problems. There's too many engineers trying to come up with, I'll make this really cool, and this will be, and then you find out, well, no one supports that material, or this is going to take an enormous amount of process control. So, it's simple materials supporting a design that you have enough knowledge on the materials, how they're going to change with processing. If it's the underfill is blue, and some days it's a lighter shade of blue. Is that a problem? The operators are going to see it. So you better have answers for some of that. So some of it is just doing your background work, doing the due diligence, keeping it simple, and the days of design teams doing something, throw it to the wall are gone. Good companies, good organizations, there are manufacturing design teams are talking all the time at the start of a design all the way to the end of manufacturing. And when they do that right, that design is fully mature almost immediately. Don't need to do anything. Quality takes care of itself. So that'd be the number one, is you just don't pick materials randomly, and hope is not a strategy, as they say. Let's not hope they work.
Yeah. So you sort of touched on this already, but do you have any other stories of things you've learned on the job that they don't teach you in the textbooks or you don't learn at school?
It's not quite, but it's close. I think the biggie is that I was lucky. The materials, the MSc department, materials and science engineering at Iowa State, is very small. So you really talk with all your professors. And Dr. Verhoeven, who actually figured out where Damascus steel came from, one of the most widely read papers in the TMS organization in their magazine, he had always said that school teaches you how to learn. Now, in metallurgy and material science, we're a little better off than some of the engineering disciplines, because periodic table is periodic table. Unless it's getting really weird, nothing's going to change there. But still, that isn't what we use necessarily out in the industry. So a lot of it is just knowing the resources. Where can you go? You've got the base. You can get on the online and look up databases and things. I think the neat things is what your mentors show you. There's a couple of old government publications, a couple from the late 1960s. One of them from Redstone Arsenal that has every combination of materials you can think of, looking at the corrosion potentials. You couldn't pay for that study today. They took 12 different types of aluminum and coupled them with everything and then measured what happened. And none of that material is in the electronic databases. No one's taken the time to take those documents and scan them in. So finding some of those unique pieces of data. I remember the person I turned my job over to, Tim Pearson at Collins Aerospace, came in one day and he needed one of the properties for a silver solder. And it was some weird, just off the shelf, never heard of this. You couldn't just look it up he tried. He went online, he looked and said, he came in frustrated and said, I need this property for this solder alloy. And I reach up and grab out of my library a book that looks like Moses wrote it, and flipped to the right page and said, here you go. And 2 things out of that. One was, how did you remember even where it was? And luckily, my brain functions somehow strangely. But the bigger thing was I knew where to look and I knew where it was. And it just happened to be something that's not found out there. And that's what mentors can do for you. That's what your industry contacts. If we'd been stumped, I might have given a call to Dr. Paul Bianco or somebody else in the industry and said, hey, I'm looking for this. You have any clue where I might find it? And 9 times out of 10, your industry buddies will say, hey, I know exactly where to find that. Excuse me.
It's not all on Google.
Not all on Google. And some things what's on Google isn't quite right.
Exactly.
So we have to be skeptical.
Yeah, what shows up on Google is what has been SEO optimized to show up on Google. And
Exactly.
If you're looking for something obscure, good luck. So maybe the AI chatbots will help us in the future once they get fed enough information, but I don't think we're quite there yet.
And for AI to work, it's got to be in the database. So, you know, I think we're going to understand just how limited our databases are and how we need to improve them.
Yeah. It's a whole new world out there these days. I really am excited to see how technology continues to evolve. So let's talk about, I want to hear interesting stories from your career. Any narrowly missed disasters or frantic attempts to solve a problem or unusual finds along the way? What do you got?
Well, there's 2, and they both revolve around BGAs. The first one, there was a lot of controversy in the 2000s about, where people had started applying X-ray to assemblies because you can't see a BGA solder joint. And people are like, how am I going to understand its quality? And how we can cross-section it. And now the board I just made is completely useless. So that wasn't going to be an avenue that we could go down. And so someone said, well, X-ray. X-rays worked for many years. Getting the medical X-ray equipment tuned over to electronics wasn't that difficult. And so lo and behold, we started seeing voids. And oh my God, literally the proverbial industry lost its mind. And the first thing is with an X-ray is my mentors taught me, well, oh, look, I see a void. That's bad. No, that's different. It's our jobs as engineers to understand, is that good? Is it bad? does it mean a thing? And so when we saw voids, it's like, wow. And there was a group put together by the J Standard 001-610 committee to go understand what is the requirement for voids. Please bring us data. They made a plea to the industry. So Rockwell Collins and Lockheed Martin and a number of people got together. We built boards. The first boards I built 40 assemblies at Collins, 250,000 solder joints, and the number of voids that were bigger than 10% were 10. I could count them on both hands. And that was embarrassing because, I can't use these boards. They're not going to help me understand the question. So then you got to go to management and say, can I have more funding? Because these boards aren't going to work, but we can use them for other things. So I got myself out of that. We partnered up with a couple of the solder manufacturers. And as you know, the solder suppliers know exactly through their chemistry and their research what enhances voiding or what doesn't enhance voiding. And so we got a solder paste that was never going to make the market because it made voids like there was nobody's business. And we created our voids. We did all the testing and we put together the paper. We knew we had the information and putting together a presentation. And I went, and of course, we had teamed up with Dage. They had done the X-ray and they measured everything at 30% of the X-ray image area. And of course, we validated all that by doing cross sections. And it just seemed weird because 30% of the X-ray image area was like 60% in the solder joint. And I made up a nice cell that didn't explain anything. And I'm literally one day away from submitting it to SMTAI for documentation and to go out and make the presentation. And Tim Pearson, my co-op at the time, looked at it and said, Hillman, you got really bad algebra. Did you ever go run these numbers? And sure enough, if you just use good old plain algebra, 30% of the X-ray image area is almost 2x in the actual solder joint itself. And so we made up a beautiful slide to do that. So yeah, I narrowly dodged having demonstrated my embarrassingly poor math skills. It's just like, wow, really? Are we
And
going to
what
do
would have
that?
happened if you did that? If Tim didn't catch it?
Thank God Tim caught it because, again, my mentors had taught me that we want people discussing the results. If you make a presentation and they're discussing your methodology, you're done because they don't believe your results. And so that would have made a question about, well, how did you calculate this? Where is this? I could have explained my way out of it, but just having the doubt there, that would take away from the final message and the data in the presentation. So luckily with Tim catching it, stronger presentation, that data went on, we presented it to committee, presented to the industry, and sure enough, what we have today is 30% maximum void in a BGA solder joint. And once that came out and was published as part of the J001 standard, we quit talking about it. We don't talk about it anymore. It's just amazing how a little bit of data and putting it out there can change what the industry does. And of course, now we're having the same discussion about voids on the thermal pad of bottom terminated components, BTCs. And luckily, because we knew what we did with BGAs, the data has been pretty solid, and shortly that's going to be solved. And I don't think we'll go through that same discussion. I think the industry will move past it quite quickly. But yeah, that was embarrassing. That was not good.
It was almost embarrassing.
Oh yeah, as it was holy cow. Let's not ever do that again. Because yeah, it's the reason I'm a material engineer. You don't use a lot of math. You use a lot of material properties, and so it saves me from demonstrating my poor math skills.
So let it be known, kids, math is important.
Those, y equals mx plus b. We all remember doing pages and pages of that. And lo and behold, what do we do every day when you run Weibull charts and do things?
You find the slope and you find the intercept, and you
exactly. So there are things that we do take out of our educational backgrounds, but a lot of it is just applying what we know and how do we put that onto the problem and see what we can do.
Yeah, I always find it interesting. So I have come from the land of physics where it had gotten to a point where it seemed like everything that could be figured out had been figured out, and anyone doing research is poking at some tiny obscure corner. But in industry, and in this industry, there are still so many questions people haven't answered, because in order to do the study, you have to have the funding, you have to convince someone you need to do it and actually do it and present it and share it. And I guess, what do you have to say to that in terms of what you've seen in terms of industry research and the importance of investing in even just simple experiments to really pin down some of the low-hanging fruit that no one has quite resolved yet?
I'm with you. I laugh when I see someone like, what do you mean there's no data on that topic? Why we all know that, well, that's just a given. What do you mean there's no papers on it? And so, okay, we'll solve that real quick. I've always viewed that academia does the science and then industry does the applied science. We don't, I always loved it. Our call said, we're going to go do research. And I said, really? What do you consider research? Well, we're going to go to understand the hardness of a stainless steel alloy. And I said, okay, how are you going to do that? Well, we're going to get one and test it. And they said, from how many different suppliers? Could that make a difference? I don't know. Does it? How many different lots? They don't produce one lot and we're good for the rest of history. They make a different lot of stainless steel daily in some places. So how they make that metal? How does it change? What's its processing? And that's what academia does for us. They give us the base principles that we as industry then go apply. So you could say we do applied research, we do applied science, but again, a lot of the basics, why do we get head on pillow? A lot of academia, the CAVE consortium, the CALS consortium, Universal consortium, they can go through and show us why does this happen. solder suppliers do a lot of base research and tell us why things happen. Even the INEMI group does that kind of thing. Once I know how they happen, okay, now I work with AIM or I work with somebody else. How do I fix that? How do I stop this? Maybe it's that AIM's going to give me a new formulation. Maybe I have to go tweak my reflow profile because I can't have something happen at, between 60 seconds and 90 seconds. And that's what we need to do. We can't just rely on answers straight out of academia. Industry has to do some work. And I feel sometimes that management doesn't understand that. Well, just take it from AIM and use it. You know how? Yeah. I always
Well, it's
love,
like in the real world, there's so many unknown variables interacting with what you're doing, and you can't account for those with a nice clean experiment. You have to just do it the way it should be done when you're running it, and then let all those unknown variables do their thing, and then see what comes out the other end, right?
right. And the variables that we can usually lock down, these variables don't really matter. I remember a co-op, we brought in a new solder paste. We're looking at some type 6 paste. And I said, have you figured out the reflow profile? I said, oh yeah, it's on the tech data sheet. And I just kind of giggled. He said, what's so funny? I said, so you're getting this from company XYZ. Do they know what our reflow ovens look like? Do you know how many zones we have? Do they know if we use nitrogen or not? And he goes, no. So what makes you think that profile and that technical data sheet is exactly what we want to use? And it dawned on him, it's a starting point. And now we need to apply our knowledge of our process and then go finish out the work. And that was one of the neat things working with the co-ops. You could see those bells and whistles kick over from what they had learned in school to now what they're learning in industry. A lot of fun, a lot of way. And I learned from them, the things they would bring, like, wow. The best one I can remember is we were working down at our Corville facility, running a design of experiments, trying to understand some flip chip solder joints. And I asked my co-op, I said, would you go please write down the reflow profile? Because I don't have a way to record it today. I didn't bring my memory stick. She walks up and brings out her camera phone, takes a picture, takes that, downloads it. And I looked at her and said, well, you didn't write anything down. It says, it's in an Excel spreadsheet sitting in your inbox in your email right now. Okay, I have a lot to learn. And that's just, the younger generation understanding their new tools that we have and how to apply them. And, like you said, AI may allow us to do many things that my generation doesn't get. We didn't have them. We don't understand it. So we'll see where that goes.
Yeah. So in your time in industry, and what have you seen different individuals or companies doing wrong? Like, what is an example of a situation or a repeated situation you've seen that people just go about something incorrectly and it never works out well?
Sometimes, a lot of times, it's just making assumptions. They make bad assumptions and they didn't do anything. I think two big areas are root cause analysis. What I always liked is we get called down to the floor. Well, this VGA's got a bad solder joint. I said, really? How do you know that? Well, I press down with my finger and it works. And if I let up with my finger, it doesn't. I said, have you been to metrology? Is your finger calibrated? And they looked at me like, what? And I said, how do you know the solder joint? That's an observation. It's not root cause analysis. In that case, of course, the next line is, so I know it's a broken solder joint because when I resolder it, now it works. And I said, no, that's an observation. What was actually happening was the microvia in the BGA pad was broken. And so when they pushed on it, the pieces of copper connected, and now the world is happy. When they resoldered it, they filled up the broken gap where the microvia was. Now the microvia could talk. It passed signal just fine. 6 months in the field, not so much. And so, that was a painful lesson for that product team to understand, really got to do root cause analysis. And ball grid arrays really caused a problem for the industry. We, for the first time, couldn't put an iron on a solder joint. We couldn't see the solder joint. We had to trust process control. And as they came into the industry, that was hard. That was hard for people to open up their comfort zone Don't understand. I have to completely live off that. And it actually, the needle swung too far. I know people that x-ray every single ball grid array on a board. And, nowadays, most assemblies have at least one, if not three or four different ball grid arrays. How much time does that cost? And I said, hey, good statistical control says, have you ever found a problem? No, they always look good. And you're still x-raying every single BGA. Why? I said, you have established process control to demonstrate with this process that you are going to make a valid solder joint. Quit doing the inspection. That's what we learned. And yet we don't let our comfort zones expand to include what we technically know we should do. So that's the biggie, is not doing, just really good root cause analysis and leaning on process control. The other is, I argued many times when we were publishing papers with some of our lawyers that, well, we can't tell them what underfill we're using. Why? Well, because then they could use it. I said, do you think that just because we put an underfill on a paper, they are going to go and just start putting it on product? Do you think that's the wisest choice someone could make? And there are people that do that. I feel bad for them because they haven't done their homework. You need to qualify a material. And so we routinely put our materials in. Yeah, maybe someone could use that to shorten their matrix, but maybe they have a different application. Their matrix needs to include other things. So I don't think by telling people what materials one is using is giving away the keys of the kingdom, because there's so much more work to do. You and I would team up. If I'm going to use a solder alloy from AIM, I'm going to go to you and say, here's what I want, here's what I need. Let's go run some trial boards. Hey, we saw this. I want to know its interaction with cleaning. I want to know a number of things. And you can only do that by using your process with your AIM's material. I can't get that out of paper. I can't get that anywhere but going and doing the work. You've got to do the work. There's nothing simpler about it. And you see some people taking shortcuts both in root cause analysis and material qualification and validation. And those two things tend to come back and bite you if you're not careful.
Yeah. Now, what have you seen people doing right? I wonder if you have any stories where you really were saying to yourself, wow, these guys have it figured out.
I think the number one, there's a lot of different things, and some of them I won't talk about to protect the innocent kind of thing, but involvement with industry consortia. You might go and pay $50,000 to be part of a consortia, but that $50K turns into $200K when you look at all the other information. And most consortia allow you to have a pet project so that you can focus on something that you want focused. But all the other companies have their same thing. And that collection of things, the things I have learned, especially out of the INEMI group, where they have looked at literally starting in 2008 to current day, the evolution of our SAC, our silver alloys up to the generation 3. What did that all mean? And someone said, well, wow, all the solder vendors are putting their alloys in. Isn't that allowing us to go, contrast and measure and compare? I said, yes, it is. It doesn't mean it's right for your application. Just because I'll say Inalot is better, it always wins. Inalot is a very beautiful alloy. It's very hard to manufacture. Is that in the Weibel graph that got published? It has a lot of voiding issues depending on your process. That's not in there. So there are a lot of things in the industry consortia. You have to do your homework, but it allows you and it allows the industry. I know from the INEMI work, most of those solder companies, now that they see what's happening, they go back and they talk to their head metallurgist and they have ideas on how to improve products and change products. And I think that's the power of being in a consortia. It's not giving away secrets. It used to be that, the consortia wouldn't, we'll wait 3 years before we publish. And then we'll only give away certain details. You can backwards engineer anything. We have the tools today to go in and look and figure out how a epoxy is comprised, what's in a solder, what's in a laminate board. It's when I know it. My mentors taught me those who know something 6 months ahead of everybody else have the advantage. And so by being part of the consortia, you know some of this new and exciting information 6-8 months before the paper comes out. And so you have the advantage, even though, yes, competitors are around. My competitors at Collins were around, but we all apply that differently. So I think that's what people do right. And it's sometimes hard to sell to management. We're going to go spend $65K or $100K in a consortia, but what was the leverage? And when did we know this information? And how did it help us? And a lot of people are just doing things on their own or pulling back out of consortia, and because of budgets and the economy. And I think that's the wrong direction to go. I think they're losing out rather than, they're being fiscally, financially savvy, but they're putting themselves behind the information curve. It's a bad place to be when you're trying to be in a competitive industry.
Nice. So wrapping up this episode, do you have any sort of final words of advice for anyone working in electronics assembly? Do's and don'ts, things to keep in mind?
The biggest one is don't do things in a fire drill. We tend to have a lot of pressures. Management wants an answer today. We're being penalized because we're behind on deliveries, or we've shut down the customer's program because this device isn't working. And the usual answer is, well, let's just change this, or let's go change this. There was a famous quote written on one of our grease boards that says, "We don't know what to change, but we better go change something anyway." Really? How much more complicated do you want to make this problem? And so I think the real thing is have patience, work diligently, but you've got to apply science, and go through the motion. And if a DOE, a design of experiments, is going to take a week, then it's going to take a week. And I think the neat thing is when you talk to a customer and you explain what you're doing and give them the rationale, they're perfectly happy. They understand why, okay, the product's not going to work for a couple of days. They can't, I can't give you a board that now functions because I have to understand it. The last thing you want to do is tell a customer you have a solution and that solution goes down the toilet because you didn't do your homework. And that's happened. People have endured that kind of pain. You lose credibility with the customer, you lose credibility in your organization, and you don't want to do that because getting your integrity back is hard to do, especially with the customers. So it's patience. It's fighting with management sometimes to have them understand this may take some time. Maybe we can do something interim in the meantime, but you can't, time is time. No one has got that time machine to go fix these things instantaneously. So that's the number one. I think that's the thing that hopefully people can embrace. And people are doing that in industry. It just takes a lot of backbone, takes a lot of willpower.
Yeah. Well, thank you so much for talking again and sharing your insights. Stay tuned for more episodes in the future. We will have one more episode with Dave, and then we will be talking to other experts in the future. Until next time, everyone.
Thank you.
We hope you enjoyed this episode of Industry Insights with AIM Solder. Don't forget to subscribe to our channel and follow us on social media for updates and new content, or visit aimsolder.com to learn more.